Alrighty, howdy folks. Section 5 of chapter 16, and this is on something called curl and divergence. I can guarantee you, pretty soon, no matter, no, I take back guarantees. Maybe I could only guarantee that if you were to take any fluids class, you are bound to see these terms curl and divergence. Yeah, that's a guarantee. Even I think you guys in EE, when you do fields, electric fields, magnetic fields, Maxwell's equations, you will bump into curl and divergence. All right, so I figured one good way to talk about this curl and divergence is to get you to recall all the kinds of derivatives we have learned about. Recall all the types of derivatives we learned so far. Okay, can you go through this? Can you recall when was what kind of derivative you learned about? I'm not talking about derivative of specific functions like what's the derivative of sine x or x to the n or something like that. I'm talking about, where did we learn these concepts? Well, we first learned about derivatives of single variable functions like y equals f of x, right? So, f maps R to R. In a way, what is this function f mapping? You were to give an input, which is a real number. It produces an output that is also a real number. That's what this is saying. Okay, f maps R to R. The fancy phrasing is actually R is the domain and this R is the codomain. But essentially what it means is you give a real number as an input, you get a real number as an output. That's in those kinds of situations, we learned about the derivative being just y prime or f prime of x, and that's nothing but dy dx. That was our first introduction to derivatives. Then this was, of course, in Cal 1. But then in Cal 2, we didn't learn about any derivatives almost till the end of the semester. And when we got to the end of the semester, we had things like parametric curves. What were parametric curves? Well, parametric curves gave us an opening into some kind of different kinds of curves. For example, for quite some time, we knew only about functions as y equals f of x or x equals f of y. What was the difference between y equals f of x and x equals f of y? Well, y equals f of x passes the vertical line test, and x equals f of y may fail the vertical line test but has to pass the horizontal line test, right? That's how we distinguished. Now the question comes, what if a curve doesn't pass either a vertical line or a horizontal line? For example, a circle. Fails the vertical line test, fails the horizontal line test. So can we not do calculus on stuff like that? On curves like that? Can we not even talk about those kinds of functions? And parametric curve said, not to worry, you can. Basically, treat that as x equals some function of some parameter t, and y as another function as a function of parameter t. So x itself is R to R. That is, you give t as a real number as an input, and you get a real number as an output. I could have said f or x, it doesn't matter. Okay, f maps R to R and h maps R to R. Okay. Okay, in that case, for parametric curves, could we find derivative dy dx? The answer is yeah, we can. dy dx happens to be dy dt over dx dt. As simple as that. You know y is a function of t, so find dy dt, straightforward. Similarly, find dx dt and take the ratio of dy dt and dx dt. Ta-da, you got dy dx. As if like the dt's cancel and you get dy over dx. Right? Okay, then what happened? We had to come to Calculus 3 to learn about a few more things. We started with, when it came to functions, for the first time, we learned about what are called vector-valued functions. What are vector-valued functions? You give an input t, that's all you give, and what do you get as an output? You actually get a vector as an output, right? So basically it takes your t and figures out the x component of this vector and also figures out the y component. They may be completely different. This is x of t and y of t, and you get a vector as an output, right? You give r as an input, but you get r2 as an output. Okay, and did we learn about derivatives of such functions? The answer is yes, we have. R prime of t, piece of cake. It simply, well, is the derivative of the x component, comma, derivative of the y component. There was no big deal to it at all. But it's an introduction to a new concept. We can learn about the derivatives of vector-valued functions. Okay, then what happened? Then we learned about these kinds of functions. What are multivariable functions? Z equals f of x comma y. We can make it into f of x comma y comma z and all kinds of things like that, but let's just stay with two dimensions. Z equals f of xy. Then the question became, are there some derivatives? What's with the r here, man? I should fix that. That's f. F is mapping r2 to r. Samuel. Sorry about that. Okay. All right. So this should be f. My bad. I may have copied from the previous one, but forgot to change this. Okay. In this case, we learned that there is this thing called partial derivative, and said, if you have z equals f of xy, you can find partial z with respect to x and partial z with respect to y. Those are the kind of derivatives we'll learn later. And after that, we learned about what are called directional derivatives. If f is the differentiable function of x and y, then f has a directional derivative in the direction of any unit vector u given by ab. The x component is a and the y component is b, and it is a unit vector. That means square root of a square plus b square better be equal to 1. In that case, we call the derivative as d sub u. It's a directional derivative along u of this function f. And that turns out to be just f sub x of, meaning we have f, partial f with respect to x, figure that out, multiply by a, and figure out partial f with respect to y, and multiply that by b. That's what gives you your directional derivative. Right? Okay. And then we got into something called gradient f or del f. That's the other kind of derivative that we learned about. Okay, what in the world was that? If f is a differentiable function of x and y, then the gradient of f or del f, and we write that as vector del f, and is given by del f is partial f with respect to x, I, plus partial f with respect to y, j. Notice here the derivative is a scalar. Do you agree with that? When we say du of f is a function of x and y. The directional derivative du happens to be a scalar quantity. F sub x evaluated at some xy multiplied by a, the x component of the unit vector. That's just telling you which direction you want this directional derivative from towards. And so this is two scalars adding up to give us a scalar. Whereas when we get to the gradient or del f, even though f is a scalar, del f is actually a vector. Okay. Now the question is this del f related to this du? Answer is yeah. Basically, if you want this derivative, then take del f and dot it with the u vector. That's it. This is what we learned. This is another kind of derivative. Cool. So I like to summarize. When I was a student, this is what I always did. Yeah, I learned so many things. Let me pause and try to summarize. And I felt that in this class, we could use some summary like this. And that's why I created this. And let me be truthful. I did that because I wanted to do it for myself. I just wanted to understand this whole thing. And so I said, yeah, let me first think through and write down all the things so that I can see the pattern. Okay, this is what we learned first, and then this, and all that. And especially so because now we are about to get into, while we did all of this, what about the derivatives of a vector field? Okay. Why did a vector field f of xy, or should I say xyz? Well, the ijk it's got, that's interesting. So its components are just dependent on x and y, but it's got three components, all the ijk components. Okay, what about derivatives of vector field like this? And the answer is, here is where we need two new quantities called curl and divergence. Let me ask, I don't know, why? What's the problem with this? Okay, let's ask, does it make sense to say ddx, just the regular derivative ddx of this vector field? Nope. Oh, okay. Can we say partial with respect to x of this vector field? That kind of no. Okay, del, how about del? Can we say del f? Right? Let's recall what del is. So del f. So I'm saying instead of a lowercase f, can I have the vector field f here? Del f? Would that make sense? The answer is no. Why not? Because del is a vector and our uppercase f is a vector field. A vector of vector? Vector? That doesn't make sense in this class. When you get to tensors, yeah, vector is perfectly all right. But right now, no, it doesn't make any sense. If you have a vector and you have another vector, the product of that can only be either what? A cross product or a dot product, right? And that's what curl and divergence are about. So if f of xy is equal to this, then curl f is nothing but del cross f. Okay, del cross f. Del is that operator, partial with respect to xi plus partial with respect to yj and so on. And that, if you take the cross product of that with this, you get this. Or cross product automatically means I'll show you the matrix determinant version of it pretty soon. Okay, but it turns out to be this. And del dot f is what the divergence is. So curl is del cross f, divergence is del dot f, where both f is the vector field. Okay, and that turns out to be partial p with respect to x plus partial q with respect to y plus partial r with respect to z. Partial r with respect to z. So, come on, Sammy. Sorry, guys, I goofed. Samuel. So what is my problem? I gotta say z there, z here, z here, comma z there, and I better copy all of this and paste here and make it bigger. Okay. Yeah. Hopefully that fixes it. All right. F of x comma y comma z. All right. I'm sorry, guys. So if f of x comma y comma z is that, and this is given by this, and partial r with respect to z. Okay. So if f is a function of three variables that has continuous second partial derivatives, theorems now. So if f is a function of three variables like this, no, if lowercase f, it's not a vector field. Okay, then curl of del f is equal to 0. Now let's first quickly ask ourselves, does it make any sense to say curl of del f? Okay, that's a question that you should really ask pretty much all the time. What do I mean by that? Curl is that operator curl operates on a vector f, right? Curl f means curl of f, and f better be a vector. So when we say curl of del f, is it the case that del f is a vector? Answer is yeah, it is a vector. So operating curl on that vector is perfectly legal. And it turns out curl of del f will always be equal to 0. I can say that, or I can actually prove that instead of making a mere assertion. And the proof is not very difficult at all. So, for example, curl of del f, curl of something, isn't that the same as del cross that whatever that stuff is? So del cross del f. Okay, del is nothing but ij partial with respect to x, I partial with plus partial with respect to yj plus partial with respect to zk, right? So that's what I wrote. And then del f is nothing but partial f with respect to x partial. So if we were to evaluate that, the claim is it'll turn out to be 0. Okay, what do we do? And determinant of a 3 by 3. I times this minus this times this. In this case, you don't say times, you take the derivative. Second partial f with respect to y and z, y first, z next, minus partial with respect to z of partial f with respect to y, so z first, y next, minus, because j, now we are expanding about this, so the second one has to have a minus, -1 to the first row, second column is this element, so -1 to the third power is -1, so we have a negative here, and cross out that row, cross out this row, and cross out that column. This times this minus this times this. I applied all of that. Okay. Now, I'm saying this is equal to 0. Is that true? Let's check. What does Clairaut's theorem say? It says if f has continuous second order partial derivatives, second partial f with respect to yz is the same as second partial f with respect to zy. Right? If you change the order of differentiation, shouldn't make any difference. Well, that means this right side quantity is exactly the same as the left side quantity, making this go to 0. Similarly, these two are equal, they go to 0, subtract, they add up to 0, these two add up to 0, and that whole thing is just 0. So curl of del f is equal to 0 by Clairaut's theorem. Next, then curl of, what did I do? It's the same thing. I have no idea why I copied that again. Theorem. If f is a vector field defined on all of R3, whose component functions have continuous partial derivatives and curl f is equal to 0, then f is a conservative vector field. Now, that is a pretty powerful theorem. I'll tell you in just a second why. Let's look at it. If f is a vector field, then, and curl of f is 0, then f is a conservative vector field. You remember that conservative vector field? Conservative vector field in 2 dimensions, we would call, I have it here. So recall that if f, the vector field f is pi plus qj, and that's a vector field defined on R2, then figuring out whether f is conservative or not meant that we needed to figure out whether partial q with respect to y is equal to partial p with respect to x. That's how we checked whether or not a vector field f in 2 dimensions was actually conservative, right? But the question is, in R3, meaning if you have pi plus qj plus rk, then how do you know whether the vector field is conservative or not? That verification is not so easy. And that's where this this theorem comes to rescue. And it says, you got a three-dimensional vector field, eh? Then just figure out curl f and see if that curl f is 0. If it is, then f is a conservative vector field. Cool. All right, so I'm not going to prove that. But if f is pi plus, this is another theorem. Okay. Earlier, we had curl of del lowercase f. Curl of del f was 0. But now this theorem says the divergence of curl of f, divergence of curl of f is also 0. Okay. Now, what is divergence? Divergence of something means del dot that something, right? So clearly, divergence of curl of f means del dot this curl of f. Curl f is nothing but del cross f. So that's what I wrote here. So del dotted with del cross f is guaranteed to be 0. The proof, again, I do have a proof, which is just simple plug and chug stuff. Del dot with del cross f. Del is just nothing but partial with respect to xi plus partial with this thing, dotted with del cross f. If you do that matrix, the determinant of the matrix turns out to be this guy. And so I'm taking the dot product of this with this. How do we do that? Well, this times this, the I component of the first vector times I component of the second vector, plus j component with times j component, and so on, right? So that's what I did. Partial with respect to x of. When we say times here, we actually mean of the derivative of the first component plus partial with respect to y of the second component, and so on. So what does it turn out to be? Second partial r with respect to x and y minus second partial q with respect to x and z. Okay, how do we take partial with respect to x of this minus this? Distribute partial, second partial x, second partial of r with respect to x and y, and so on. Okay, now this turns out to be 0 is the claim. On what grounds? Notice there's a second partial r with respect to x and y, and by Clairaut's theorem, that's the same as second partial of r with respect to y and x. This is positive, whereas this is negative, so these two add up to 0. Second partial q with respect to x and z, there's a second partial q with z and x, negative, positive, add up to 0. Similarly, p with respect to yz, p with respect to zy, they add up to 0. So just the sum is just 0. So divergence of curl f is also 0. And you will learn all kinds of useful applications of these concepts. What exactly physically does all of this mean? Yeah, by the way, physically, the curl f, pay attention to this, please. Imagine you have a bucket of water, and have you ever done this? Put your hand in that bucket of water and spin it. Give it a twirl. Keep on spinning it and let go. Then you will notice that the water spins in whichever direction you spun it, right? If you look at that water that is swirling round, rotating about the axis, about the center axis, ask yourself, could you represent the velocity of each of those particles as a vector field? Yeah, one would be going to the right, and another one would be going down, a third one to the left, and in fact, if you had spun it in a clockwise direction, things would be tangential to the velocity vectors would be tangential to circles, right? So your vector field would look like that. If you were to take the curl of that vector field which is in this case the vector field is a velocity field, velocity vector field, then you will see that the curl F is what indicates that this fluid is actually turning, is swirling or rotating. And oftentimes in fluid mechanics, we are interested, is this fluid spinning, turning or not? On the other hand, if you were to look at a lake that is just flowing, or a river that is flowing, the velocity field, everything is pointing in the same direction, and so there would be no curl. The curl of that field, that velocity vector field would be 0. So curl indicates rotation. Cool. All right. What else? Yeah, one last definition, I think. There's something called del square, which is nothing but del dot del, and that's the Laplace operator. And del square f is second partial f with respect to x plus second partial f with respect to y plus second. So you will learn that there's something called diffusion. This is the diffusion equation. What's a diffusion equation? What is diffusion? Imagine you have a bucket of water. I don't know, for some reason I'm talking about buckets of water quite a bit. Okay, so bucket of water and nice clean water, and you drop some dye, okay, some colored dye. What happens? Initially, the dye will flow through the fluid and cloud, it sort of like looks like a cloud going down, and then, well, leave that alone and come back after an hour. What would have happened? The whole dye would have diffused in this water, bucket of water, and the whole bucket of water would have dye, instead of being clean and clear water like it was before, would have changed its color to whatever the color of the dye is. So when you initially poured the dye, what happened and what happened at a later time seems to be completely different. What happened there? Well, engineers and physicists say that diffusion took place. The concentration of this dye just diffused out throughout the whole thing, and the equation that governs the diffusion is this guy, in fact. Cool. All right, so Laplace's equation is this, and the Laplace operator applied to a vector function del square f is just nothing but the question is, let's ask, can we apply del square to a vector function? I thought you said you cannot have a vector and a vector next to it, man. No, man, I don't quite have that. Yes, it is true that, pay attention to, sorry. Yes, it is true that del is a vector. But the question is del square a vector? No, it's a del dot del. So that means the dot product we know is always a scalar. So del square is actually a scalar. Can you apply a scalar to a vector? Yeah, you can. And it turns out to be, all you need to do is take each of these components and find del square p, and that's what you get if you figure out, if you want to write this as using the Laplace operator del square. Cool. All right. Vector forms of Green's theorem. What all of this does is, learning about this curl and all of this is, the Green's theorem can be applied even to 3 dimensions, but you need the concept of curl. It turns out if you have 3-dimensional stuff and you want f dot dr, then let's say the curve is actually 3-dimensional. It's not a plane curve, but actually it's a curve in space, right? Well, you can do this. Curl f dot k dA is what you need to find. All right. So with that, let me solve a couple of problems, and that's all I need for you to know. Know those theorems, know the definitions, know the theorems, and know how to solve a couple of these problems. And I'm a happy man so far as this particular section is concerned. Cool. Find the curl and divergence of this vector field. Okay. Curl. Simply the determinant ijk partial with respect to x with respect to y with respect to z of each of these components here. Okay. I times partial with respect to y of this guy minus partial with respect to z of this guy, so on. So patiently I did this. What's partial with respect to y of this? Square root of z is a constant. So 1 over 1 plus y, the derivative is negative 1 over 1 plus y square. And so negative square root of z over 1 plus y, the quantity 1 plus y square, minus, there is no z component, so that just goes to 0, I, and so on. Okay. And when you simplify, this is what you get. That's it. Can you do a problem like that? I'm sure you can, right? That's, if you know that, I'm a happy man. I'm telling you, seriously, in this class, in this section, this is all I want you to know. Similarly, divergence of f, del dot f. Del dot f should be straightforward, right? Partial with respect to x of the x component of f, and plus partial with respect to this, and you know how to. 1 plus z is a constant, so derivative of square root of x is 1 over 2 square root of x, so this becomes this, and plus da da da. Done, right? Yep, that's it. Determine whether or not the vector field is conservative. Yeah, what do we do? F, we are given this, conservative. I don't know, you remember, if curl is 0, curl of f is 0, then the vector field is conservative. So what this means is we just need to evaluate the curl of this, and that turned out to be not equal to 0. Okay, and that means f is not conservative. Cool. Ta-da! That's the end of this section. If you know those definitions, you can solve these two problems, problems like these two problems. I'm a happy man. Cool.